All right, it is the appointed hour, so we shall begin. The ranks look a little thin. I don't know. That quiz wasn't that bad, was it? The grades weren't bad in general. Okay, so assignment. I have emailed you this document. I could email it again if somebody needs it, but I have already sent it out, I'm pretty sure. This document is pretty good and it's pretty detailed. So I want you to start reading it. And let's see here. Seems like chapters 1, 2, and 3 are really pretty quick. We can look at them real quick. If I can get to them here. Yeah. Intro. Yeah, there's one. That's not too bad. 2. And even 3. 3 is not much. Identifying properties of steam. You should be good on that. So let's see. Let's read chapters 1, 2, 3. And we need to get into 4 a little bit here. Steam System Survey Guide. I'll show it to you here in just a second. Let's read in chapter 4, sections 4.1 and 4.2. So chapters 1, 2, 3 and sections 4.1 and 4.2. So let's start working on those. And the document is the Steam System Survey Guide. I think the title of the file is just Steam Survey Guide. But this is, I can send it to you again, or this is also downloadable from the US DOE website. If you Google that, I think you could probably download it from DOE. It's been out there a while. Greg Harrell is a personal friend of mine. He's a great guy. He's at Milligan. He has started an engineering program for Milligan College up in East Tennessee. And Greg and I have traveled the world on numerous occasions. And we've always had a great time working together. He has provided a lot of the training that I have in doing these STEAM system assessments. So anyway, this is he's a very detailed, very thorough, very excellent engineer, and this is a very, very good document. Okay, so enough of the testimonial to Greg, and we shall proceed here. Okay, so this is where we wound up last time. So I think I have already discussed this slide, but the indirect method of calculating boiler efficiency, we quantify all of the significant losses, and in terms of a percent of boiler input fuel energy, we subtract from 100. If we included all of the losses and we did it absolutely correctly, we would get the same number as we get from the classic efficiency. But because the classic efficiency has every loss in it, because you're measuring fuel in and steam energy in the steam out, and so it by definition contains all losses to the system. In this approach, we have to pick the losses that we want to quantify. And so, you know, you're probably not going to pick all of them. So I guess theoretically, the classic or direct method of boiler efficiency calculation probably should have at least a slightly lower value because here we're probably, in the indirect, we're probably not going to quantify quite everything. Okay. So ASME has the power test codes, and they have PTC 4, which is for large steam generating units. And so this is, I have a copy of an older version, which is smaller. I have a copy of this someplace. It's about 300 pages. And so it's really too large to use for pedagogical purposes. I may send you the older version, which was written in the probably 1950s sometime, but it's still is still very pertinent. It's not quite as up to date as this one, but it's a whole lot shorter. It's about 70 pages instead of 300. So I kind of prefer working with that one, really. So we can we can discuss a gross efficiency that includes auxiliaries. And by auxiliary systems, we mean like fan energy, pumping energy, other sorts of energy that's required to operate the boiler. But if you do the fuel efficiency, which is kind of what we're talking about, it has been the output of the steam energy divided by the heat input, that is a fuel efficiency. But there are procedures to include the fan energy and other types of stuff, which we will not spend much time on in here directly. So PTC4 has the two different approaches to efficiency described in it, the direct or the classic method of calculating the boiler efficiency, or the energy balance or the indirect method. This is cut and pasted out of PTC 4.1, which is the older version of the power test codes for boilers. But I put this in there because it details 15 different losses that can in general be calculated on a boiler. And of course, then that document goes in with equations and procedures and all of that. It tells you specifically what to measure and how to measure it and how to do the calculation of the loss, because these PTCs get used for warranty purposes. If there's a lawsuit over performance of the boiler steam generator, this is the procedure that would be used to test it, to see if it was actually capable of doing what it's supposed to be able to do when you sign the contracts and wrote the check for, you know, $100 million for a big, huge boiler. And they say, hey, that thing's supposed to be able to make 100,000 pounds an hour, or 1,000,000 pounds an hour, and it can't. We can't get that much out of it. There's something wrong. Either they didn't put in the right boiler or something's not operating correctly. And so these things can wind up in lawsuits and that sort of thing. Anyway, so this is a very official set of calculations and procedures in order to do the evaluation. And so you can say, I mean, some of this stuff we'll talk about. That top one, I'm just going to hit a couple of them. Unburned carbon in refuse. So if you're burning coal, you typically pulverize it. You may or may not pulverize it. Bigger boilers tend to pulverize it, like face powder. And so all that gets blown into the combustion chamber and ash comes out. Well, when you capture the ash, you can send it out for analysis. And if it still has a lot of carbon in it, guess what? That's fuel that you paid for that you didn't release in your boiler. You didn't burn it effectively. So something's wrong. It could be your pulverizers are not working correctly. Could be, you know, there could be a lot of things. Could be the burners aren't functioning properly. But so evaluating that loss will tell you something about the operating condition of your particular boiler. Moisture in the fuel. If your coal or your wood or something comes in wetter than it's supposed to, you're putting more water in the boiler, you're going to have issues with it. Carbon monoxide. If you stick a combustion analyzer probe in the stack and you measure a bunch of carbon monoxide, that's carbon that didn't get burned to CO2, which is what you're trying to do, which releases a whole lot more energy than carbon that's burned into CO. Because CO is still a fuel. It has a heating value and you're throwing it up the stack and is poisonous. So there's a lot of really good reasons to not put CO up the stack. unburned hydrogen, unburned hydrocarbons, all of this stuff. Soot blowing, pulverizer rejects, the rocks and things that come spitting out of the pulverizer that it can't crush up. All this stuff represents a potential loss of energy from that control volume. Okay. But like I said, we're going to do 3 or 4 of these things in some detail on the rest of it. I just want you to know that this stuff is out there. And I probably will email you out a copy of PTC 4.1 for your library. We spend some time in it in the steam power plants class. Okay. So let's look at shell loss. So PTC 4 has a calculation procedure to estimate boiler shell loss. One thing that you can do, you can shoot the sides of the boiler with an infrared camera, and any hot spots will show up. And the infrared camera manufacturers have software, so I can look at the side of a boiler and I can get in their software and I can select that side of the boiler, and that software will give me the maximum temperature, the minimum temperature, the average temperature across that face of the boiler. So if I take my tape measure and measure it, I've got the surface temperature. I can measure or assume an ambient temperature in the boiler room. I can calculate a convection coefficient, and I can calculate the heat loss from that side of the boiler. So I can shoot this side, that side, the front end, the back end, the top, and usually you just kind of let the bottom go because you can't really get to it. And so you can run those calculations, and you can actually get a hard number, you know, as good as your convection coefficient is, which, you know, those things are always a little bit squirrely. So that's one way to do it. A lot of times the shell loss is estimated different ways. Here is just kind of to give you some rules of thumb. This isn't very good, but it kind of gives you a low end and a high end to estimate a shell loss. And so we've got some different categories of boilers and different sizes. So we've got fire tube, we've got small fire tube, water tube. We got 3 different water tube categories, kind of small, medium, and large, okay? And then for the fire tube. The smaller water tubes would be probably on the low side. The smallest ones would be maybe 10,000 pounds an hour, and on the high side of the small category, up to 100,000 pounds an hour. So the maximum shell loss would be about 2%, and that's percent of fuel input energy, down to a low side of about 0.3%. So your shell loss is probably going to be inside that range for that size of boiler. Okay, our medium-sized boilers would be 100,000 pounds to 1 million, and the shell loss drops. And what's happening is you have so much more energy going through the boiler coming out in steam that the percent that you can lose from that surface goes down. Okay. So that's going to be on the high side 0.6%, down to about 0.1%. And then on the really large boilers, 1 million to 10 million pounds an hour, like 0.2% on the high side, maybe 0.1% on the low side. And the fire tube, the small one might be down to 1,000. And I changed this number. The presentation that I emailed out had 40,000 in there, but I know of 2,500 horsepower boilers, which is like 86,000 pounds an hour. So someplace around 90,000 is probably the largest that you're going to find. And so that range would be like from 1% down to 0.1%, something like that. Just to give you an idea of what is kind of possible or what you should expect. Okay, so our example boiler that we had up there last time it was making 100,000 pounds of steam, and it had a capacity of 120,000 pounds. And so, you know, if you do an ASME type investigation, the radiation convection loss from that boiler is estimated at about 0.5% of the total fuel input energy. Okay, if you recall, we had a 77.1% efficiency, something like that on it, and it was costing $13 million a year to operate at $10 a million BTUs in fuel cost. So if you take 0.5% of 13 million, you get 65,000 a year. So it just gives you, you know, some kind of an idea of the magnitude on a boiler, 100,000 pounds an hour. That's about what Tennessee Tech runs, something like that. We've got a 2,000 horsepower, which is 68,000 pounds an hour. And when it gets cold outside, they have a couple other boilers over there, and I think they have to run more than one. So on the high side, and plus when we have the new fitness center and this new science building online, our load will probably go up to 100, a fairly common load will probably go up to on the order of 100,000 pounds an hour. So, you know, you think about Tennessee Tech and, you know, we're heating all these buildings around here and all that sort of thing. So our shell loss over there is probably someplace between $50,000 and $100,000 a year. Now, is there anything we can do about that? Well, you know, we're going to talk about that here in the next couple of slides. Full load radiation convection losses are typically, and these are some more typical numbers, less than 1% fuel input energy for water tube and less than 0.5% on fire tube. In general, for the same size of boiler, the fire tube has an advantage because the hot gases are embedded inside the tubes, whereas on the water tube boiler, the hot gases actually touch the shell. And so there's a much larger temperature difference to drive heat out of the water tube boiler. Okay, this second bullet is, you know, pretty important in the discussion of shell loss. The shell loss percent increases as boiler load decreases because shell loss magnitude is essentially constant. So what in the world is that trying to say? Well, what we're saying is once you have the boiler up and operating, it's hot. If you run it at 25% load, that shell's hot. If you run it at 100% load, that shell's hot. And so the number of BTUs per hour or kilojoules per hour lost from the surface of that boiler is pretty much constant once it's up and going, no matter what the load is. And so if you think, if the number of BTUs lost is constant, but at full load, I'm putting way more fuel into it, that's going to drive the percent down. If I'm only operating at 25%, but the shell loss is the same, I'm dividing by a number that's 4 times smaller on the input side. That makes the shell loss 4 times greater than it would be at 100% load. So that's where those numbers come from. So if we're 0.5% at full load, we go to 25% load, we can roughly multiply that by 4, and it goes to 2%. Okay? Now, the number of BTUs lost is the same, but as a percent of the fuel input energy, it changes because the amount of fuel input changes with load. So that's kind of the concept there. So what's that tell you? You don't want to operate 3 boilers at 1/3 load when you could operate 2 boilers at what, 60% load. You could shut one down and you would eliminate that whole shell loss and you could still produce the same amount of steam. Okay, so that's really our biggest opportunity is if you go into a plant and they're operating 3 or 4 boilers and the load is not, not very high on each boiler, say, well, could we not turn off one and operate 1 fewer boiler eliminate that complete shell loss and let the other boilers just operate at a higher percent of fire. So that's what you look for. I was in the Brigstone plant in Warren County. And Brigstone Warren, they make tires. So they're cooking tires. They're curing rubber with steam. Well, it turns out, and I didn't know this until I went down there, they're running several boilers very lightly loaded. They're running 2 or 3 boilers at 25% load. 25% load. And you go, hey man, why are you running 3 boilers 25% load? Why don't we just run 2? We could probably just run 1 and shut off 2. They say, you don't understand. So when they get a load of tires in there and start cooking them, they control temperature by steam pressure. If something happens to a boiler and they lose steam pressure or they change steam pressure, they get a change in temperature. Well, if they get much of a change in temperature, it can potentially affect the quality of the tire. Louder? Okay. And so they are extremely paranoid about their boiler pressure. So engineer Glenn comes in, sees all this, and calculates, you can save $30,000 a year in shell loss if you, I don't know, go from 3 to 2 or 2 to 1, I don't remember, because I mean, the steam load was relatively small even for 1 boiler, and they were running multiple boilers. I said, well, this is an easy $30,000. And they looked at me and they said, no way. No way are we going to do that. If we have an aberration in steam pressure, we have to track all this additional paperwork on every one of those tires from cradle to grave. And it's a big pain in the patootie. And we're not going to do that. And Mr. Consulting Engineer, you could just move on to your next idea. I said, but, they said, end of discussion. Shut my mouth off and went on to the next thing. So, you know, what looks like an opportunity is different depending on what seat you're sitting in. If you're the production engineer that's sitting there, I got to have constant steam pressure. I don't care. If it costs a little more money, if it costs $30,000 extra a year, I don't care. We're making lots of money on tires. We can afford it. If you're the energy efficiency engineer, you're looking at all of these things going, hey, oh man, we could do this, we could do this. And so it's a battle. It's a battle when you get in. Now, sometimes you win and sometimes you lost. Well, I lost at Brigstone, and probably rightly so, you know. I mean, I'm there for 2 or 3 days a week, and they're there every day of the year cooking tires. So, you know, they know a whole lot more about it than I do. But anyway, that's an example of where I thought I saw an opportunity to monetize shell loss by operating 1 fewer boiler. The other thing you have to be concerned about, let's say if you went from 2 to 1 and the 1 was operating at 90% load. Well, if you get an increase in steam demand and you're already at 90% load, you've only got an extra 10% you can go up. And so your pressure, you know, if that demand is more than that, then you can't meet it and your pressure will fall. Because it's going to take you a while to get a boiler online, especially if it's cold. Another thing people do is they will maybe operate 2, but they'll keep a 3rd boiler on hot standby, which means they fire it intermittently just to keep it hot so they can put it online quickly if one of the others goes down. And there's things you can do to make that more efficient. There's things, it's called a drum heater. And what you can do, instead of actually firing that boiler, you can put a heat exchanger into the steam drums and just pipe some steam off of the header into those drums, into those heat exchangers in there, and keep the drums hot. That'll keep the boiler hot enough that you can fire it quickly, and you don't that's much more efficient because those boilers making that steam are already operating well up in the load range, and they're more efficient. If you just intermittently fire a boiler, you're basically throwing that energy away just to keep the boiler hot. So there's better ways to keep boilers on hot standby than intermittent firing. But that's a little bit of a side issue at this point. So the last main bullet there, the primary opportunity in this area is to reduce the number of boilers in operation to reduce the total site shell loss. Stack loss impacts must be considered. And so as you change firing rates and all, you can change the stack loss, and that has to be considered in this. We'll get to stack losses here shortly. Okay, so here's our summary slide where we just kind of summarize the concepts here. That's an infrared image. Where was that? That may have been Campbell's Soup over in North Carolina. I spent a week over there a number of years ago. But you can see that those white spots are pushing 275, 280 degrees. That's too hot. What that tells you is the fire brick, the refractory on the inside of that boiler has broken down. There's cracks in it, and the hot combustion gases are getting up next to that metal on the outside. I've seen temperatures as high as 400, 450 on the side of a boiler, and that's way, way too hot. In some cases, if it gets too hot over a period of time, it will actually basically burn a hole in the side of the boiler. You can have the hot gases coming out, which is not particularly good, So you got to be a little careful. Spots like that really don't represent that much of an energy loss. That's more of a maintenance item that needs to be attended to. So as we say, you should expect 120 to 180. Depends just on how good the insulation and refractory is on the boiler. So reducing boiler load can present an opportunity. Comment on that. Okay, so that's the radiation convection losses. Let's go to blowdown. Okay, so blowdown is water that we drain out of the system, typically the main steam drum, in order to keep the amount of dissolved minerals to a controllable level inside the boiler water. Okay, if they concentrate too much, they will become insoluble, and they will plate out as a scale. And that scale has a very low thermal conductivity, and it's like putting an insulating layer on the water side of the boiler. It's like you've slapped insulation on your boiler. So here you are burning all this fuel to transfer all this heat, and you have, in effect, if you scale up your boiler, you've in effect put insulation on the inside of your boiler that's going to retard the heat transfer. So that's not really too good. So, I mean, what happens? Well, the source of all of these minerals is the makeup water. Because, we take water out of the ground, we buy it, maybe we have our own wells. And when it comes into the plant, it has minerals in it. We clean it up to a certain degree, depending on the pressure. The higher the pressure the boiler is, the cleaner that boiler water has to be. But we can't get all of them out of it. So there's still some in there. So you've got makeup water coming into your system, bringing a steady supply of minerals in, and then it goes into the boiler and we produce steam. Well, very few minerals carry over in steam. So, minerals coming in, pure steam going out, where are the minerals? Well, they stay in the water. And so the concentration is going to continually build and build and build and build if we don't do something until we start scaling up. So blowdown is the solution. So blowdown is the removal of liquid water from the boiler to maintain proper water chemistry. Dissolved and precipitated chemical concentrations are controlled. Blowdown is required to reduce the concentration of dissolved chemicals and keep them in solution. If boiler water chemistry is not properly maintained, significant problems will result. And I tell you, I think, let me see if I can find this. I have a video that is a borescope video taken at the Frito-Lay plant in Frankfort, Indiana, where they had scaling and they had a company come in, I think it was GE came in, ran a borescope up inside the tubes, and you can see the scaling. If I can find it, let's look at borescope. I should know where. Well, that's not doing good. Let me just look over here. What do I want to do? Steam system. Where have I done with that? Well, I should have looked this up before I came in here. Let's try it again. Ah, there it is. There we go. All right. Ah. Yeah, it's been one of those days. You gotta be kidding me. Does it appear you have any honest person? Is it gonna work? Well, I guess I'm gonna have to, I'll get this thing working. I'll show it to you next time. It was a good idea. It is pretty good. We got plenty of time. Okay. So if you don't take care of your boiler water chemistry over time, you will destroy. You will destroy your boiler. First, you will destroy your efficiency, and later on, you will destroy your boiler. So water chemistry is crucial. Okay, so let's take a look. Blowdown can take several forms. Surface blow comes off of the water level, right below the surface water level in the main drum. And surface blow is meant to control the amount of dissolved solids, okay? And it can be continuous, which is what you would want. What you want is you want a sensor, and typically we measure conductivity. We measure electrical conductivity of the boiler water, okay? So let me ask you a question. If you go to Kroger and buy some distilled water and take it home, take it to the lab, and measure the electrical conductivity of the water, will it conduct electricity? It's water, man. Does it conduct electricity? Raise your hand if you think yes. Raise your hand if you think no. Raise your hand if you really don't. Never mind. I don't want to go there. Okay. The answer is no. So, you know, it's like if you're in the bathtub and your significant other wants to do you in and throw the space heater in the tub. If you're taking a bath in distilled water, you'll be okay. If you're taking a bath in hot water out of the tap, you're going to get fried. You're going to be in big trouble, okay? Because it's the minerals in the water that actually conduct electricity. Okay, so distilled water with no impurities, no minerals, doesn't conduct electricity. So an easy way to measure the overall mineral content of the water is to measure the electrical conductivity of it. And so you can get a fairly inexpensive probe and system and sensors and all those sorts of things. And so you simply have a set point on your conductivity, and that sensor goes to an automatic valve, which simply is, you know, rocking back and forth, more or less open to drain water out of the boiler to maintain your desired conductivity. Typical numbers I see, and what is this, micromoles per centimeter or something, 2,000 to 3,000, 3,200 is a typical set point on one of those sensors. And that's really that's the best you can do. Well, a lot of people don't have that. So what they do is they'll take old Joe, the boiler operator, will go in there and there's a big valve on that, and he'll go, once a shift, he'll go in there and throw that valve open and drain boiler water down the sewer, count to 10. Throw it open, count to 10, count to 5, count to 15, whatever the recipe is for the plant, shut that thing off, goes back, sits down in the control room again. They may do that once a day, they may do it once a shift. Depends on whoever is managing the boiler. And then they will take conductivity readings on every shift to look and see where they are. Well, they may have a set point of 2,500, and so what happens is when they blow that thing down like that, they'll drive it down to 2,000 or 1,800, and then over the course of the remaining shift, it'll come back up, and it may get up to 2,500, may get a little bit above, something like that, and they continually drive it down, and it continually seesaws up and down. So the result is that you blow down more water than you need to because you want to keep it below that set point. If you have a controller, you can dial, if 2,500 is your limit, you can set it on 2,400, and it will bleed the amount of water it needs to in order to maintain 2,400. And over the course of a year, that can be a fair amount of water, and that water is coming out at boiler temperature, which is pretty hot, and so there's energy to be saved there. Yes, sir?
I might be wrong, but I thought, can't you use the blowdown because it is hot? Because I know you said you actually lose energy whenever you try to use like your makeup water because it's cooler.
Mm-hmm.
So I think I read that they use blowdown.
Absolutely. Absolutely we can, and that's...
Can you also circulate it back in, or
no.
It's done? All you can do
well, you would have to clean it up. Okay. Because see, that's the reason that you got rid of it, was because of all of the high mineral content. Okay. Now, if you have a use where you don't mind having high mineral content someplace else in the plant, but you don't want to put that water back into the boiler unless you clean it up before you put it back in. But yes, you can, and that's where we're headed here in the next couple of slides, is blowdown heat recovery systems. But so you see, you know, some plants have them and they don't work right. So, and a lot of plants don't have them at all. You know, it just depends, you know, what they purchased when the plant was put in. But absolutely. Okay. That's the surface blow. And like I said up there, that can be continuous or intermittent. We'd like it to be continuous. And then there's bottom blow, which is intermittent. And you typically don't do heat recovery on the bottom because it is just intermittent, where the guy throws the valve at the bottom because he's wanting a big gush of water to take any solids that have accumulated at the bottom of the boiler or at the bottom of headers and things like that, and blow that stuff out of there. And that is done typically once a day, something like that. And it's 10 seconds and it's gone. So you can't afford to put a heat exchanger in for something that only lasts for 10 seconds. You know, it's just, it'll never pay back. So the bottom blow, we don't really try. Now, some systems will route the two blowdowns together, in which case you may be able to get a little bit of the intermittent blowdown, but you don't put in a separate heat recovery system for bottom blow. Okay. Primary control is typically based on water conductivity. I've kind of jumped ahead. Conductivity must be correlated to actual water quality through specific analysis. So yeah, and so what that's referring to is you may be controlling that valve based on conductivity, but you still need to take water samples and make sure that all of the different components in the water are within appropriate limits. And you may find that 2400 is not enough. You may need more blowdown. You may need to drive it down to 2000. Or it may be that 2400 is too much. Everything is well within limits. You can go up a little bit. So that needs to be periodically checked, weekly or monthly, to make sure that everything is staying within the right range. You know, with a detailed laboratory analysis, where you'll take samples and send it to a laboratory and you'll get a full assay on what's in there. And this shows the basic layout. That green line is coming out of the drum, goes through the conductivity sensor, and it's controlling a valve, and that blowdown, at least in this picture, is going to sewer. So we're throwing it all the way at this point. Okay, so let's do a calculation. Blowdown loss estimate for the boiler. And so this little lambda, lowercase lambda blowdown, that's the loss. And we can multiply that by 100 if we want a percent. So we take the mass flow rate of the blowdown times the enthalpy of the blowdown. So that's most likely this is saturated liquid at whatever the boiler pressure is. That's easy to determine. And then the enthalpy of the feed water, that's the feed water that actually makes it into the boiler. So, you know, at 242, we're probably preheating that a little bit. We'll talk about that in later portions of this discussion. But anyway, so 242, you'd look up saturated enthalpy at 242 if that's the temperature it's coming in. So mass flow rate times that enthalpy difference divided by the mass flow rate of fuel times the higher heating value, and times 100 for a percent. So the blowdown flow rate can be less than 1% of feed water flow or greater than 10% of feed water flow. The fuel input energy loss can be less than 0.1% or greater than 5%. Depends on how well you're controlling this. And we'll talk here in just a minute about what the parameters are. Okay, so if you don't have any sort of heat recovery system, back to our kind of cartoon or diagram of a steam system that's two-header model, high pressure, low pressure, and you see the dotted line coming out of the boilers, and that line is going down over here on the side, and it's going into a, what kind of tank is that? It's a flash tank, right? See? And so we've got flash steam coming out the top of this, and right now it's going to vent, we're throwing it away, and then the liquid that's left after the flash steam leaves is just being discharged to the sewer. So that's kind of what a lot of people do. That's not really very efficient, but you see that's pretty common to see a system set up like that. Okay, now, so you can do a calculation for the system, you can do a calculation for the boiler. It depends where you put your control volume, okay? So if you put your control volume around the boiler, what you have feed water in, blow down out, and steam out, right? If you put your control volume around the whole system, what do you have? You've got, well, you can keep the steam internal, but you got makeup water coming in and you got blowdown coming out, okay? So it depends where you want to draw the control volume. If you put it around the boiler, you get this, but if you put it around the whole system, it's the same equation, but all of a sudden this becomes the enthalpy at which the makeup water comes into the system down here, instead of the enthalpy of the feed water coming in up here. And so what that does is this needs to be the enthalpy that the steam system, the steam system takes it from that temperature and all of the heat is supplied by the steam system. If it's heated beyond that point with waste heat or something, then you should use the higher temperature. But see, so we're saying here 75 degrees, that the steam system has to take it from 75 and use it in the whole system. And so that's the delta enthalpy that we have to spend fuel for. Okay, and so if you do this, you're going to get a larger loss because obviously the enthalpy of 75 degree water is a whole lot less than the enthalpy of 242 degree water. Okay, so blowdown amount is primarily dependent on water quality, how good is your makeup water, and your boiler operating pressure. The higher the pressure, the more likely it is for this scale to form. And so your water has to be purer and purer and purer. So the utility company, the TVAs of the world, operating 1,800 pounds or 2,400 pounds or whatever, they have to have extremely pure water. Water that, yeah, I mean, you know, we take water and drink it out of the water fountain, right? Well, we used to, until they disconnected all of them. But, you know, you go out and go home, get a glass of water and drink it. Well, you're drinking all that crud. You can't put that in a boiler, but you put it in you, works just fine. So these boilers are much more delicate. So that water has to be cleaned up. The other thing that happens is there are chemicals, oxygen scavengers, and chemicals that are put in there to help prevent corrosion, keep oxygen. High temperature oxygen is extremely corrosive. So you really have to virtually eliminate the oxygen content. So you can get a certain amount out in the system, and the rest of it, we put in some chemicals called oxygen scavengers that will grab onto that oxygen and keep you from, pitting, having holes, corrode into your boiler or into your metal surfaces. Yeah. Yeah, that's a softener is kind of like the first stage of water treatment. That's what low pressure systems have. That's what tech has. You go down there and you go in the boiler house and they got these two big big circular tanks, and they've got some kind of water softeners in there, and it pulls out a lot of that stuff. But say they're only running 100 max 110 pounds of pressure, so their requirements are not that severe. But you get up to, 400, 600, 800, 1,000, and you got to get cleaner and cleaner and purer and purer. I've got a slide in here that gives the different concentrations that are acceptable at different pressures. And you see the water has to get better and better as the pressure goes up. Okay, blowdown management typically takes the form of improved water quality, improved blowdown control instead of manual, go to an automatic controller, and heat recovery. Okay. Blowdown management begins with measurement. Typical blowdown amount is estimated from boiler water chemical analysis. Whoever sells you your boiler chemicals, the water treatment, Nalco is one of the big ones. There's a number of good. Tech's got, is it Nashville water treatment or something Tech uses? And they're apparently quite good. Andy Loftus, the campus engineer, is quite happy with his water treatment people. But those people, they know the bleed rates, like in the makeup water and all that stuff, because they know how much chemical they're selling. And so there's a definite relationship. The more makeup water you bring into the system, the more chemicals you have to use. So over the course of a week or something like that, they can tell you very accurately what your makeup water rate is. Good place to go to get information. Okay, blowdown rates can be less than 1% by mass in high quality water systems, are higher than 10% in low quality water systems. The other thing that we'll get into here is the last bullet on this, is how much of the steam that goes out, it condenses in the system. What percent of that do we get back? Because the assumption is that condensate is going to come back and it's going to be pure. Unless you've got holes in heat exchangers or something, or somehow you're getting crud into your steam lines or your condensate lines. You send out pure steam, it condenses, that water should come back to you and be pure and good and ready to use again. And it may even have it should have some temperature on it too. So the higher the percent of condensate return, the less makeup water you need, the less makeup water you need, the less chemical that you need, and the more efficient you're going to be. So your blowdown rates will go down. So what do we say, that middle bullet? Most facilities require makeup water softening as a minimum form. The best is reverse osmosis, reverse RO systems. Reverse osmosis is a membrane-based system that forces the water through membranes that capture almost all of the minerals and crud. RO systems are very good. They require high pressures. They require, 300, 400, 500 PSI. So they got pumps. They'll have, 20, 30, 50, 75 horsepower pump to force that makeup water through these membranes. It cleans all that out. And the membranes have to be changed ever so often and all that. So they're fairly costly to operate, but they do an excellent job removing crud, minerals, and all the stuff from the makeup water. Okay, so let's look at our example boiler. I think most of this we had up there before. So our heating value, that's our higher heating value, 23,311 BTUs per pound, or 1,000 BTUs per standard cubic foot. Steam conditions, 400, PSIG 700, making 100,000 pounds an hour. Boiler rating is 120,000. Feed water, 600 PSIG at 242. There's our fuel supply, 149,000 standard cubic feet an hour. $10 a million BTUs, and we calculated the operating cost at 13 million a year. Okay, so this is not very complicated, but this is a good trick to know. So chemical concentrations such as chlorides and other chemicals can be measured to determine the blowdown rate. For the example boiler, the chloride concentration in the feed water was measured at 15 parts per million. Chloride concentration in the blowdown is measured to be 250 parts per million. So basically that ratio, 15 to 250 times 100, gives you 6%, and that's a good estimate of your blowdown rate. Okay? So that would say that 6% of that feed water flow going into the boiler is drained out through the blowdown line and discarded from the system. Now, it's better to do this if you've got the ability to do some of these good chemical tests and concentrations. It's also acceptable to do this with boiler water conductivity. So you can measure it's pretty easy to measure. I mean, you just get electrical conductivity probe. You can get a handheld probe. You get some of that water. It's got two electrical probes on it. You put a voltage across there, and it measures the current, and then is calibrated to read out in conductivity. So if you stick it in distilled water, guess what? You get no current, and so you get a reading of 0. If you stick it in water that's got a whole lot of minerals, you get a lot of current, and it transduces that and gives you a conductivity reading. So it's pretty easy to measure these conductivity. It's harder, if you got to do some sort of a chemical test. Take this stuff and take it and put drops or, evaluate it somehow or the other. So there you go. Say we measured the feed water conductivity to be 150, and that's micromoles per centimeter. That's what I thought. Strange unit, but that's a conductivity. And then in the blowdown, it was 2,500. So that equates back again to 6%. So you can measure a chemical species, or you can measure the boiler water conductivity. Okay, so now the blowdown flow rate is determined from a mass balance completed on the boiler. So where this little equation comes from is if you do a mass balance on the boiler, what do you got? You got steam leaving, you got blowdown leaving, and you got feed water coming in. So basically you just do the mass balance and do a little bit of algebra, and you can come up with this equation. So this will calculate the mass flow rate of blowdown based on this blowdown rate, which in this case, so we said we calculated at 6%. That's beta. We put it in as a fraction. So we got 0.06 divided by 1 minus 0.06 times 100,000. And that's the amount of steam leaving the boiler, because that's usually what we measure. Most systems don't measure feed water flow. A few do, but typically, you got a steam flow meter because you want to know how much steam you're producing that's going out to your processes. And so bingo, that's what you know. So that will calculate your blowdown flow in terms of pounds per hour, whatever steam flow rate you put in. Okay, so with your mass flow rate of blowdown, then we can go ahead and pull these enthalpies. And so the enthalpy of the blowdown, that should be, I believe that's probably saturated water. We're 400 psig, so that should be saturated water at 400 psig. And the 210 is saturated water at 242. Mass flow rate of fuel, and there's your heating value. So when we take the control volume around the boiler itself, we come out with 0.9%, or roughly 1% of the total fuel input energy resides in that blowdown stream. So we're throwing away 1% of the energy we purchase and put into the fuel in the blowdown. However, if we take a larger view and look at the whole system, we're really making up with 75-degree water. And so the equation should be basically the same, except for that second enthalpy. Instead of 210.42, I look up saturated liquid water at 75 and put it in there. And now I get 1.7% of my input fuel energy is being spent on the blowdown. That's the amount of energy I'm draining out and throwing away. Okay. And the system, so that's the system impact instead of just the boiler impact. So this is the one that you would, because that's what you're spending on it, but you can draw that control volume either way. Okay, boiler blowdown thermal energy recovery typically focuses on continuous surface blowdown. So you see, if you're doing intermittent blowdown, the first step you need to do is get to continuous, because you can't get any payback to purchase a system, and this system may cost between $50,000 and $100,000 to put in your heat recovery system. If you're only draining water out of the boiler for 10 seconds twice a day, you know, that heat exchanger is going to sit there dead for almost all the time, and it's not going to do anything for you. So the first thing you got to do is, instead of doing it on a 10-second interval, you need to have a continuous flow. The continuous flow is going to be a much smaller flow rate, but it's going to be all of the time. And so then you've got a continuous flow. I got something I can work with. You know, if it comes in 10 seconds and it's gone, forget it. I mean, you can't do it. So the first thing you got to sell them on is going to, you know, a continuous blowdown, and then you can start talking heat recovery from it. Okay, so, and the continuous surface blow comes out of the top drum. Recovering energy from blowdown can dramatically reduce blowdown losses and release water chemistry requirements. So if we put in the right system, we can get almost all of this energy and capture it. Well, so what do? Well, instead of going straight to the sewer, we put in two components. The overall system, the full-blown system, has a flash tank, and it has a heat exchanger, a liquid-to-liquid heat exchanger. So that high-pressure saturated liquid goes into that flash tank, and depending on where you pipe it to, depending on the pressure at this low temperature, I mean at your low pressure source, you know, this could be, what are we saying, 400 PSI? This could be 20. If you got a 380 PSI drop, you're going to get probably 15 to 20% of that mass is going to flash into the vapor state, and you can take it and it'll be pure. It'll be pure, because again, when that steam comes off of that liquid blowdown, the minerals stay behind. So it'll be pure, and you can take it and use it at some low pressure. You can put it in a low pressure header. You can pipe it to the deaerator, which we'll talk about, which requires low pressure steam. So you can usually find a place to use that flash steam. And then what you have left is whatever pressure that tank operates at. As soon as that, as that 400 PSIG saturated liquid goes in that tank, that pressure drops, that temperature drops to the saturation at that lower pressure, right? Because you've got both phases present in that tank. So if that's let's say that's a 20 PSIG tank, so 20 PSIG plus say 15 for atmosphere, 35. So the temperature of that liquid would be the saturation temperature at 35 PSIA out of the steam tables. Well, that's still going to be 250, 240, 250, 260, 270, something like that. That's pretty hot to just throw away. So then we run it through a heat exchanger, and we take our makeup water or some other liquid stream that we want to heat up. And so we want the makeup water to be a continuous stream, and we want the liquid blowdown to be a continuous stream, because we want that heat exchanger working for us every hour of the year, you know, being productive, recovering energy for us. Okay, so more details. So there's a better picture. So that blowdown comes in, saturated liquid at the drum pressure, hits that 20 psig tank, low pressure to low pressure steam system, and the liquid goes through the heat exchanger. I got makeup water coming in at T3, going out at T4. Liquid blowdown comes in at T1 and leaves at T2. So 1.7% of the fuel input energy is approximately $215,000 a year. And this loss can be eliminated by purchasing these two pieces of equipment. So this project, this is a good size system, would probably have less than a 1-year payback to invest in this equipment if they did not have it already. To put numbers to it, so your boiler blowdown at 6% was 6,400 pounds an hour. We get 23% flashes, so that's 1,500 pounds an hour. 1,500 pounds an hour is a pretty good steam flow. And that represents 23% of the mass, but 67% of the energy, because that steam is so energetic. Again, nominally, it's probably 900, 950 BTUs a pound going out. Yes, loud?
If 23% of the mass is flashing steam, they have to clean out that tank a lot.
I'm sorry, say that again.
So if that boiler tank, or where the boiler blowdown is going into and flashing into, if 23% of that is flashing into steam, are you losing a lot of what the blowdown is clearing out into that tank? Would you have to clean that out often?
Oh, you mean as far as crud buildup? Because, well, probably not the tank, but the heat exchanger, absolutely. When you select this heat exchanger, you want a heat exchanger that you can clean. Okay. Yeah, so you're right on track. You're just one component upstream. I mean, it's possible, but I'm not aware that the tanks really fill up that much. I'd say that heat exchanger's got, you know, small tubes and passages. And absolutely, because see, that stuff was concentrated when it came out of the boiler, and we're going to flash off 23% of it. What happens to the concentration in the remaining, what is that, 77%? Well, it's even more concentrated with crud. Absolutely, absolutely. And so, yeah. And that shows up on a slide here in a few minutes. But this heat exchanger, it's got to be selected. Plate and frame, where you take them apart with the gaskets and you can scrub them, or a single pass where you can open up the end caps and rod out the tubes, you know, where you quickly and easily clean it. Absolutely. That's a great point. Okay. So yeah, the amount of flash steam formed is dependent upon the pressure in the boiler and the pressure in the flash tank. The bigger the difference, the more flash you get. Absolutely. Remaining liquid, so we got 4,900 pounds mass an hour, which is 77% of the mass, but it only has 33% of the energy. So if you were only going to do one of these two, well, you could put in the flash tank and you get 67% of the energy and just forget about the heat exchanger and go ahead and throw that away. I mean, you're still, you got almost 70% of it. That's something to consider. Absolutely. Okay. This is pretty much the same. We added the approach. So T2 is the leaving you know, when you size heat exchanger, you size them on an approach temperature. I guess this is the entering, the leaving blowdown water minus the entering makeup water, whatever. There's different definitions of approach, but anyway, that's a, okay, here you go. Here's the slide. Heat exchanger caution. Blowdown stream presents a significant fouling potential, even in a cooling environment. Capability of cleaning the heat transfer surfaces of blowdown heat exchangers must be provided. Straight tube with blowdown on tube side and plate and frame are the two that are recommended. Absolutely. So, you know, if you're going to do this, you would want to talk to your heat exchanger people and say, okay, you know, let's make this as easy as possible because we're going to have to clean it every year probably. Okay, so what are some interactions that we might have here? So this is where these simulation tools become pretty nice. So you see, we've got turbines. We got a turbine up there. That red guy in the middle is what a turbine turning a generator. So how can this blowdown heat recovery system affect the operation of that turbine? Well, so look at what it's going to do. So we come out of the boilers with that red dotted line. We go over to the right, and we go down to the flash tank. Okay? So we get steam out of the flash tank that goes into the low pressure header. Now, before we did this flash tank, the only way that steam could get through that, get to that low pressure header, theoretically, unless we're using the PRV, is to go through a turbine. So now we've got steam that's going directly in the low pressure header that didn't go through the turbine. So there's less steam to go through the turbine. And that's going to affect the turbine operation. So, you know, if I'm generating electricity, you see, up here, see I'm coming out. I'm coming out. That's my saturated liquid at the drum pressure. I come down here, I get this 23% of this stream goes into steam, and it goes directly into the header. So now that amount of steam didn't come through this turbine. So if that amount of steam didn't come through this turbine is not going to produce as much work. There ain't any doubt about that. So this output is going to fall based on doing this recovery. So we need an overall model of this system in order to be able to figure out the economics on this. Because yes, I get this recovery, I put less fuel in here, but I get less electricity out here. How does all that wash? You know, what's the total payback on the system? Okay. And so that's where the measure tool comes in. We can very quickly and easily do a model of this in measure and let measure calculate, because it's doing the overall energy balance and mass balance and all that stuff. And it'll tell me in short order, you know, all of those interactions. So that's pretty good. And so now this is the tool. I need to update these slides with measure. So this is a tool, a steam system assessment tool. I've still got it on an old computer, but basically Oak Ridge has taken this and programmed it into the measure tool. So now this is in measure instead of being here. So I tell you what I'm doing. I think I'm going to stop here. We're just about at the end, and I will try to get this modeled in measure. And pretty soon we need to go another lecture or so, and then we need to get you all a little homework working in measure. So if you haven't downloaded it, I encourage you to just get it, punch around on it a little bit, play around. So you guys have a great weekend, and we will call it quits for today. Thanks very much.